Let's talk about Hooke's law, energy, kinetic energy, potential energy, and force. Okay, they're all related. Force and energy are not the same thing, but they're very, very closely related. When you act on an object and do some work, you're exerting a force on it through a distance, and that causes the object to gain energy of some kind. If you cause it to accelerate, it causes it to gain kinetic energy. If you cause it to gain height, say you lift it up, then you've given it some gravitational potential energy. And if you use that force to stretch a spring or compress a spring, then you've stored some energy as elastic energy in the spring. So we actually have three different kinds of mechanical energy. We have kinetic energy, gravitational potential energy, as well as elastic potential energy. Now, this worksheet's about, elastic energy, elastic work, force, and stuff, but all of them are related. So we had the law of conservation of energy, and we're gonna use that in this. Okay, so let's go ahead and get started. These are fairly straightforward problems. These are Hooke's law problems, and Hooke's law just says that the force required to stretch a spring is equal to the spring constant K times the distance x. The force in the spring is the negative of this because the force pulls against you, but the force required to stretch the spring is this. So we're going to have the spring constant, which is 95 newtons per meter. If you look at that unit, it actually tells you it takes 95 newtons of force to stretch the spring a meter. We're not stretching it a meter, we're stretching it 0.25, so 95 newtons times 0.25 meters tells us that we need 23.75 newtons of force. Okay, and if we wanted to figure out how much work we did stretching that spring, well, this is a little bit weird because we have this graph looks like this. The more we pull this thing back, the more force we need. So the force isn't constant. So the work done to stretch this spring is not this 23.75 newtons times the distance 0.25, right? What we actually have is a triangle with a base of 0.25 meters, a height of 23.75 newtons, and if we wanted to find the work done, we'd do 1/2 base times height. So be careful when you actually are calculating the work done to stretch a spring. It's not the same thing as the force required to stretch the spring. Alright, number 2 says, a spring has a constant of 56 newtons per meter. How far will it stretch when a 12 kilogram block is hung from it? So, you know me, I like pictures. I always start with one. So here's my block right here. It's got a mass of 12 kilograms. 12 kilograms is going to be fairly heavy. That's about 30-ish pounds, right? But in newtons, we take m times g to find how much it weighs, and 12 times 9.8 is 117.6. So there's 117.6 newtons of force pulling down. So now I know F equals 117.6. I know K, the spring constant, is 56, and I'm trying to find X, how far this thing moves. So F equals Kx, or X equals force divided by the constant, and so 117.6 divided by 56 is about 2.1 meters. That's a really long ways to stretch a spring, but 56 Newton meters is not a very big spring constant. Okay. Similar problem here on number 3. The spring constant of a spring that stretches 12 centimeters, so X is 0.12, right, because centimeters to meters. Force is 24 newtons. That's a point. And we're looking for K, so F equals Kx, or F divided by X equals K. My handwriting just keeps getting better and better, doesn't it? So 24 force divided by 0.12 is 200. So my spring constant is 200 newtons per meter. So it takes 200 newtons of force to stretch that spring 1 meter. A spring with a spring constant of 144 newton meters is compressed a distance of 16.5 centimeters. How much elastic potential energy is stored in the spring? Okay, this gets back to that graph I was looking at before. Just because you've exerted a force of 144 newtons does not mean that work done is the same as force times distance, because you weren't applying that force the whole time. You started with applying 0 force, and the spring was as long as it was going to be, and then you increase the force, increase the force, increase the force. So over here, force is getting bigger, distance is getting bigger, and so you've done how much work to stretch this spring? Well, you've done the area of this graph, and so the energy stored in a spring, the elastic potential energy stored in a spring, is 1/2 base times height, which is 1/2 x. Now, since F is equal to kx, I'm going to sub that in for F, 1/2 kx, and so I get the elastic potential energy is 1/2 kx squared. Okay, and so then I say, okay, I know the spring constant, it's 144, and I know x, be careful, this is in centimeters, we want it in meters, so 16.5 becomes 0.165 squared. Okay, so 144 times 0.165 squared times 0.5 is 1.96. Remember, it's energy, so that's joules. So that's 1.96 joules of elastic potential energy. That's also how much work you did, right? That's the work energy theorem. The work done on an object is equal to the energy change the object experiences. A spring has a constant of 256 newtons per meter. That's fairly large. How far must it be stretched to have an elastic potential of 48 joules? Right? So elastic potential energy, EPE, equals 1/2 kx squared. And so 48 equals 1/2 256 times x squared. And so 48 times 2 is 96, divided by 256, square rooted, and we get 0.61. So x equals 0.61 meters, or 61 centimeters. Okay, if you stretch that spring 61 centimeters, that much work is done to it. Alright, this is an energy conservation problem. This one is a little bit more intense, but not bad. An 800 kilogram car rolls down a 50-meter high hill starting at rest. Okay, and it hits a spring at the bottom. That's right, and it squishes the spring. So up here I have an 800 kilogram car, and it rolls down the incline and hits here. If the spring has a spring constant of 300 newtons per meter, so K equals 300 newtons per meter, how far will the spring compress? Well, this is a conservation of energy problem, right? How much energy does it have up here? Well, elastic potential energy is 0 because there's no springs going on here. Kinetic energy is 0 because there's no motion up here. But there is gravitational potential energy, PE, which equals mgh, and so we take 800 times 9.8 times 50, and we get a fairly large number, right? 392,000 joules. Okay, so there's 392,000 joules of energy stored up here. Now, as it comes down that hill, that potential energy is converted into kinetic energy, right? And so when it gets down here, it's moving, and it has 392,000 joules of kinetic energy, no potential energy left. But then it hits the spring, and the spring compresses, right? Because it's taking this 392,000 joules of potential energy that's now kinetic energy and converting it into elastic potential energy, EPE. Okay, and so since no energy is lost to friction, we're going to say our elastic potential energy when the spring is all the way compressed is 392,000 joules, right? Because that spring is going to bring the car to a stop, so it has no kinetic energy anymore. And this is 1/2 K, which I know is 300, times x squared. So my 392,000 times 2, right, divided by 300, square rooted, and we get a fairly large number. X equals 51.12 meters, right? So that spring's going to compress 51 meters. It's about 60 yards. It's 2/3 of a football field. That's a long ways, but, right, you had to stop a big car. Now, this question right here, what will happen after the car has been brought to a rest? What's the spring want to do? Does it want to stay compressed? Heck no. It wants to launch that car back out, right? So it launches the car back up the hill. And since this is a frictionless hill, this would just be an oscillation. It would just keep going. It'd be like swinging a pendulum back and forth. No energy is lost, no energy is gained. It'd be perpetual motion. It doesn't really happen. There's always friction, but that's the way we read it. Now, number 7. This problem is tricky. Okay, and it's tricky because of gravitational potential energy. when you're standing on a scale, there's actually a whole series of either springs or levers or both going on in there, and those springs exert forces up to support you. So when you're just standing here, there's a couple forces going on. There's gravity, mg, pulling down, and there's the normal force, Fn, pushing up, and those forces are balanced. Well, the normal force is actually being exerted by all these springs, and so since these forces are balanced, we say a scale tells us our weight, but it doesn't. A scale tells us the normal force, the force that it's pushing up with. Okay, and in this case, the normal force does equal mg, and it says this is 700 newtons. So 700 newtons is the force. Okay. That's supposed to be an F. The force is 700 newtons. We know that this distance it compresses is 0.5 millimeters, and so we're going to go ahead and calculate the spring constant of this thing, F equals kx, and so 700 divided by 0.5 millimeters is really not very far. Okay, that's 0.0005 meters. So we take our 700 and divide it by 0.0005, and we get 1.4 million newtons per meter. Okay, so the spring constant here is 1.4 million, or 1.4 times 10 to the 6th newtons per meter. So that's kind of big. Now, when you actually jump onto a scale, okay, there's a lot that has to happen. Not only do you have to slow down and stop, but then the scale is going to support you. So when you jump onto it, the force increases until it's supporting your weight, but then it increases until it stops you, and then it rapidly decreases again. And you can feel it when you jump. You feel heavy when you hit the ground. Okay, so then we have this whole other issue that we have to deal with, because where is zero gravitational potential energy? So I'm going to exaggerate this. Here's the springs underneath my scale. Okay, when you hit this scale compresses, okay, and so it moves down, say to here. That means this scale moves through this distance x. Okay, you start 1 meter up. Okay, you hit this scale and you end way down here. Now this is where you've got to pay attention. Okay, is this zero gravitational potential energy, or is this zero gravitational potential energy? It doesn't matter which one you pick, but you do have to pick one, right? Because if this is zero gravitational potential energy, this spot actually has negative gravitational potential energy, and we got to deal with that. Okay, if this is zero gravitational potential energy, then this 1 meter is actually not 1 meter, it's 1 meter plus this distance x. Okay, so I'm going to go ahead and I'm going to call this spot my zero, because it doesn't make a heck of a lot of sense to me to have zero gravitational potential energy be below where I'm going to be. Okay, but that means I got to pay attention up here. The potential energy for this person up here is given by mgh, but h is not 1 meter. Okay, it's m times g, which I know their weight is 700, times their 1 meter they're up, plus however far these springs are going to compress, right? This distance x that these springs compress. Okay, now they fall, they hit the scale compresses till right here. Okay, and now we have zero potential energy from gravity, and all we have is elastic potential energy. So this is equal to elastic potential energy, which is 1/2 kx squared. Okay, and so my 700 times 1 plus x equals 1/2 k, which is 1.4 times 10 to the 6th times x squared. Okay, and this is going to be a quadratic formula. So 700 plus 700x equals 0.7 times 10 to the 6th x squared. Subtract that over and do the math, and let's see, we get our A term is negative 700,000 Our B term is 700, and our C term is also 700. And so we get a distance, an x distance of 0.032 meters, or 0.32. 0.032 meters. Okay. Now this is not the answer to my problem. This is how far the springs compress. Okay. And since those springs compress that far, I know the force registered by the scale is equal to kx. I can take that times my 1.4 million spring constant, and we know that this scale is going to read a very, very large number. 1.4 times 10 to the 6 times 0.032 is 44,800 newtons. Okay, 44,800 newtons of force to bring you to a rest. Okay, that is why it's very important that you bend your knees and you can allow that force to act over a very long time instead of that rapid force right when you hit.